Hello Fahima.
Yes, sir.
You can hear me, right?
Yes, sir.
Yeah, okay. So I think we'll start the class because we don't need to wait for others. I think, are you able to understand the statistical mechanics? I mean, have you seen the videos, or if you have any doubts, you can ask me till now. So, what is happening in statistical mechanics for the last two classes? Okay, fine. I'm going to start the class. Okay. See, 1 second. Hi, you can see the screen, right? Hello. Am I audible?
Yes, sir.
Yeah, okay, fine. Thank you. So this is for the week 11, and I think we have one more week. And I asked for the extra class to get my attendance. So we'll see whether you'll get one more class or not. So in the week 11 class, you have pair potential of atomic systems, pair potential of molecular systems, then coding for LJ potential, and then computer simulations, and then examples of MD simulation or the script. Then we have the tricks, which is nothing but PBC. So this is the topics which we are going to cover in this class. So, so what we discussed in the last class was the difference between difference in quantum states. I mean, quantum mechanics, thermodynamics, and the ensemble approach. Where in quantum, what we have done was we have taken the independent sorry, in the quantum, what we have done was we have taken independent distinguishable particles initially, and we started to write it as n factorial by n1 factorial, and from here we have done the approach initially based upon the microstates and all. And what we got was we found out that when we want to approach for the extensive states, extensive properties, so then what we saw was the v is converting to 2v and n is converting to 2n, but s is not converting to 2s. It is coming with some log values. So then from this we made some what you call the changes, saying that indistinguishable elements. So if it is indistinguishable elements, it's a update in the, so where we are not distinguishing any two elements. Then we followed the partition functions, and we found out that the extensive property, whether it is following the extensive property or not. So then we get s to 2s. So now once we have done with this, so then we come to ensemble approach. So the basic difference between the quantum state classical and ensemble approach was in the quantum state where Boltzmann taken was the particles are not interacting. The particles are not interacting. But in real life, whatever the biomacromolecules you have taken, it's all interacting. So that is the first approach we have taken in the ensemble. So the particles should be interacting. So then what we have done was, so we have followed the two properties. One is positions of the molecule or the atom and the momentum of the atom and how it is changing. This is what we discuss in the ensemble approaches. So we all know that ensemble was developed by Maxwell Boltzmann and primarily by the Gibbs. So what we have done was, say suppose at time t equal to 0. One second. I'm just brushing the whatever we had discussed in the last class so that from there we will continue. Say suppose at time t equal to 0, this is the state, and time t equal to 1, time t equal to 2, time t equal to 3, and so on, time t equal to m, and so on. So if I take a single state, a single micro state, where in all these we have the same number of particles, and the box size is same, and the temperature is same. So it means number of particles is same, box size is same, and T same. And then what we are finding out was the what is the changes in the inner. Say suppose you have the 5 molecules initially like this at time t equal to 0. At time t equal to 1, the system might be like this. At time t equal to x, the system might be arranged like this. So these all are happening at the constant NVT. So what we are studying was, we are studying the, so what we mean by ensemble was, collection of systems which are macroscopically same but with different in microstate. So what do you mean by microstate here was, we are changing the position and the momentum of the molecule. So that's what we are discussing. If you take macroscopically, if you say this one and this one, this one and all the things, if you see the size and the number of particles, everything is same, and together by doing for the longer time, you will get the ensemble approach. So suppose we have, if I give you example, like say suppose you have macrostates of, say you have 100 macrostates which run at the constant NVT, and you have 1000 macrostates which are run at the constant NVT, and you have 1 into 10 to the power 4. I'm increasing 1 0. So these all are the different macrostates we have under the same constant NVT. So what will be the difference was, the partition functions whatever you are going to calculate, or the say thermodynamic properties, it will be much more, will be in line with the theoretical if you increase the more macrostates. I mean if you have the more macrostates. So your understanding why I'm saying was, say suppose in the first state you have like the system W, and in the second microstate you have this W, and the third microstate you have again this. Assume that instead of like this I am writing alphabet. Assume this is the protein. So the protein initially like this, then it changed to like this, then it like this, then it like this, then it came again like this. So like this, if you take 100 structures, sorry, 100 structure, the probability of getting the stable state, assume that this is a stable state, or might be this is the stable state. If I say this is the stable state, probability of getting stable state out of 100 configuration is very less compared to the probability of getting at higher rate, means higher microstates. So that's why if you have the more microstates of the similar values, then you have the probability, because that's where the ensemble formula comes. We understand this concept, why we need to have the more macrostates compared to why not 100, and why we need to have the 10 to the power 7. If you have 10 to the power 8, it's still fine. If you have 10 to the power 9, it's also fine. So you understand the logic? Am I audible, right?
Yes.
Yeah. I mean, if you don't understand, then I'll explain it again in the another terms. So just let me know, because this is an important topic you need to understand.
So can you repeat again?
Okay, say suppose you understand the you understand the macrostate and microstate, right? So
Yes.
so now say suppose you have one macrostate, and this is a second macrostate. Macrostate, assume that there are macrostate is nothing but one box with say suppose 5 particles. Okay, this is the initial configuration. I mean, this is one macrostate M1, and M2 we have the same number of particles. So can you tell me what is the difference between the M1 and M2, and I will write M3 also. So assume that the box size is same. This is M3 and M4 is. So can you tell me what is the difference between different macro states? Is basically the alignment of the number of particles inside it. Okay, so if you have done the last week assignment or anywhere, so you have seen that you have given one macro state. So suppose in the quantum state they said you have different energy levels, and assume that this is one macro state. And if I ask you to put, no, this will get confuse you. One second. So you understand, right? So what I'm saying was, we have 4 macro states. So here, if I talk in the macro state level, M1 is equal to M2 is equal to M3 is equal to M4, because in M1 we have number of molecules and the volume and the temperature is same as, okay. But if I come to macro state, M1 is not equal to M2 is not equal to M3 is not equal to M4 because of the alignment. Here what we are considering was the proper Ri is nothing but the position of the atom or say molecule, and Pi stands for the momentum of the molecule. So you understand that, right? The basic difference between the macrostate and microstate in general.
Yes, sir.
So now what we are going to do was, say suppose you have 100 and the meaning of ensemble is collecting all the microstates. I will write it in another way: collecting all the macrostates which are similar but different in its microstate. Okay, so suppose here you have, if I talk about the ensemble in this condition, you have the 4 ensemble, okay, 4 macrostates. In the same way you can have the 100 in the same way, you can suppose ensemble, I will writing ensemble as ensemble 1, we have ensemble 2, so now here we have 100 microstates, here we have 1000, here we have 10 to the power 4, here we have 10 power. So what is ensemble was, so now, so why we are doing this was to at the end to get the thermodynamic properties. So this is our basic understanding. We need to have these thermodynamic properties and we need to have the partition function. So here the thermodynamic property is total energy. We need to get these values, right? That is our end goal. So and you can get the original value. I mean, say suppose with respect to the experimental papers or with respect to the experiment which is going, because this is all the simulation what you are talking about. So then we can get only if the probability is more. Say what do you mean by probability is more is, say suppose you have the ring, okay, the ring shape is this, okay, and in the second macrostate the ring is like this, and the third macrostate the ring might be like this. In the fourth macrostate, the I'm talking about the ring which is placed on the hands. In the fourth macrostate it will be like this. So it can take any form, but you know that if I add all the things, and the total energy will be constituently, the total energy will be considered majorly by this shape, right? So if you have these shapes more, say suppose if these are the shapes, 90 are this type of shapes and 10 are different types of shapes, so what you will get was the total energy will be more on this and less will be on this, so there will be domination of this energy. Okay, so that's why the probability is more important here, the probability of attaining the stable state. So that if you have taken the 100 microstates, 1000, 10 to the power 4 and 10 to the power 5 states, you know that the probability will be comparatively more compared to the 100. Okay, and if you have 10 to the power 6, it will be more comparatively here. So you understand the topic what I'm talking when talking the ensemble and the probability.
Yes.
So now we have we have ensemble average. So because we have all the different types of now I said energy, right? So that's what ensemble average. Uh, so ensemble average will be change in the position of the nth particle, n particles, and change in the position of the n particles of the system of this with respect to the probability of. So this is the formula. So I will rewrite it. We are writing two integrations because we have two terms. Change in the positions of n particles change in momentum in n particles of, so of which, suppose if I given the ring and if you are saying the ring positions on the xyz coordinates and the momentum, and it is a ring, right? So of the ring and the probability of attaining the stable state. So this is the formula for ensemble average. And now if you are talking about the probability, so this is nothing but kBT by partition function. So now the H is nothing but total energy. So we all know that the partition function is nothing but okay. So this is the equations which you don't need to remember. So if you remember this equation, for probability what we are doing was, for probability we are adding the maximum energy which we can obtain from the macro states. So now we have ensemble average and we have the time average. So what do you mean by time average is, we say that if you run for the long enough the system, say suppose I have run for 1000 microseconds or say 1000 nanoseconds, and I am saving each one from how to say it, 1000 nanoseconds for each 1 nanosecond, then I will get 1000 microstates. If I take this each with 1 picosecond, if I take this data, I will get 1 into 10 to the power 6 macrostates each with each with 1 nanosecond, and then it will be 10 to the power 9 picosecond. So we will get 10 to you can see the difference between 1000 nanosecond and 1000 picosecond. So if you run long enough, then we can easily say that ensemble average equal to time average. So you don't need to do the differences in this. So then the formula given for the time average is T equal to 1 to m. So it is how many frames you are taking basically, and you are calculating the change in the momentum at that. So this is the time t, and then this is the time t. See, suppose what is the time t equal to 0 and t equal to 0, and then t equal to 1 to 3. So this is nothing but ergodic hypothesis, this one. The spelling is ergodic. So instead of getting these ensembles, so what he done was, here we talked in the microstates, right? So now he can tell it in the picoseconds time, 100 picoseconds, 1000 picoseconds, 10 to the power 4 picosecond, 10 to the power 5 picoseconds, and 10 to the power 6 picoseconds. And if you run longer enough, then we can say that the ensemble average is nothing but the time average. So once we are done with the ergodic hypothesis, so then what we have is partition function. I can call the partition function so the term which we are getting here was h of r comma n is nothing but the total energy of the system. So once we are talking about the total energy, we have kinetic energy plus potential energy, and we know that kinetic energy is nothing but half mv square. It can be written as p square by 2m because p equal to mv, because we are dealing with the momentum terms. And then, so we know the partition function, right, which we are talking from the starting. So now we have the potential energy u of r. So now say suppose we have taken a box, assume the particles are not interconnected. It means there is one atom here, one atom, one molecule, and say atom molecule, just assume that they are not interconnected. So we have these molecules. So can you tell me the potential energy here? So what are the potential energy which is exerted by this system? I think, yeah. So you are getting the point, right, for where I'm going. I'm just explaining the last class so that the today's class will be very much easier. So if you're talking about the potential energy, u of r of the given system. So I am saying this is A, this is B, so this is C. Forget about, don't assume the sizes are equal. I made some mistakes, so once again. So just assume so the particles. So we have different particles. So now if I'm talking about the UR, so now we have this molecule, right? Just assume this molecule. This molecule can move freely, right? This molecule can move, so this can go any direction. And everything can move, right? Because we are, that's what we are talking, right? We are talking that change in the momentum and the position. Say suppose and assume that the molecule is moving from this side, or maybe suppose this molecule initial position is this, it moved to this, and maybe here, and then maybe from there to here. Maybe it's not bonded, it's like positions, change in the positions. And the second molecule is also moving from this direction to this direction, maybe like this. So it can move any direction, right? So we are taking the difference between this. So now the potential energy will be, say suppose this molecule is going to this side, or this side, or this side. There will be force exerted by the pressure walls. So that will be the UR plus, I mean the single molecule, any molecule, say this molecule also, if the molecule hit the wall, there will be a force acting on that particular molecule. So that is the individual property. And then we have two molecules, so these two molecules can collide. So there will be a force between interacting between these two particles. So then it will be sigma I equal to 1 to n minus 1 to sigma j equal to I plus 1 to n u I comma j of r. So then we have three particle system. So now there is a one particle system, and there is two particle system, then there is three particle system. What do you mean by three particle is, say suppose there is a first molecule, and there is second molecule, and there is third molecule. So I am taking 1 2 3, this is 3. So now one can collide with two, one can have the force of interaction with these two, and then two can have the interaction with these two. So it has three particles interaction, plus and so on. So in general terms, we are not talking we will neglect the higher terms, because this much far we can't go through the simulation, because this is not necessary. So mostly we will carry out the single particle and the double particle. So any doubts of UR? So basically U of R equal to, this is nothing but this is plus U12 of R plus higher bonded interaction so this is equal to total energy. So any doubts in this?
No.
So once, yeah, so up to here at the last class. So now in this class we will talk about the pair potential of, or for atomic system, then pair potential for molecular system. So now what we are doing was, I have the atomic system. Just assume that I have two molecules, and I need to find the pair atomic. So suppose if you see this formula, I am writing the formula here. The total energy will be U of R bar plus U of 1 2 of R. Okay, just assume like this. So now we are talking about only this term. We are not talking about this term. We will discuss it later. So now we are talking about this term. Okay, we are talking about the only pair. Okay, pair potential is nothing but 1 2. So we have two atoms. So now there are different types of pair potentials are already defined. So first one is hard sphere potential, So this is all were discussed in the class by sir. So what he is telling was, so if you have two molecules, say suppose this is the first atom and this is the second atom. This is the center of radius to R and this is the R, and now this particle will move like this until it will reach to here. Sorry, there won't be any bonded. Yeah. So this is sigma 1 2. So this is sigma 1 and this is sigma 2. Okay. So this, the whole distance from here to here is atomic diameter. And for the hard sphere potential, it was written that equals to infinity comma 0 for r less than sigma and for r greater than or equal to sigma. So you understand the equation, right? So what it says was, so r is nothing but this one. R is nothing but the distance between two molecules, distance between the two atoms. So what the hot sphere potential was, it has taken only two cases, whether either less than or greater than or equal to. So if it is greater than or equal, just assume this is the case, this is the potential energy and this is the distance, and say assume the one molecule is here, the constant one, and initially we kept the second molecule here. So now the R is greater than the, see now, so the sigma is not, yeah, the sigma is nothing but this one, right? So it means, say this value is, I can put it as, assume some value. This will be when the two atoms are close only, we will get the sigma, right? So this is the sigma. So now the atoms are very far, so it means you will get the 0. So here the value will be 0. So it will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So it means the molecule is going from here. So it moved to here, then it moved to here, so then it moved to here, then it moved to here, then it moved to here. Just assume like this, yeah. So the molecule is moving. So now for this case, so the u of r will be, so from, if there is lf r, it will be dot dot. See, it is on the 0th line. You should remember this is the 0th line. So I'm just making it for the understanding. Okay. So once it comes to this position, when the two atoms are nearer, it will repel. Okay, that's what it's saying. It will directly goes to the infinity. So this is nothing but the sigma. So that is, here there is one atom, and there is here one atom. You got the point, right? For the hot sphere potential. Any doubts in the hot sphere potential?
Yes.
Yeah. So once we are done with the hot sphere potential, so the next one is square well potential. So what this guy has done was, this guy has taken the three properties for the u of r, infinity, minus epsilon, and I think 0. So this is for the gamma, and this is for the less than r sigma 2, and this is r less than sigma 1. So now what it is taken was, so now say suppose if you know the hydrogen bond, or if you take any C bond or C double bond C, so you know that there is a distance between these two molecules, right? Say suppose the C is maintaining some distance with the C, such that say suppose there is a O and the hydrogen modifies a OH, there is a bond, okay? It's not like we are not writing like this, right? OH. So there is a certain equilibrium distance such that they both can have certain energy to break the molecule. If you say that, you will say, right, in the chemical reaction you need to break the molecules, or in the drug design also we will see that there is a bonding affinity, binding affinity, we will say that. That is because it can form a bond. Okay, that is the equilibrium distance between these two molecules. So basically we'll call it the attractive force. Okay, so now if I say that now the value will go like this. It will go to certain extent and then it will go like this. So because it is then it will come like this. So this is basically sigma 1 and this is sigma 2. So this is epsilon, and we are getting in between for the sigma 1 sigma 2 we are getting the epsilon. Epsilon is nothing but the attractive force. So then we have the another term, soft sphere potential. So here he mixed the both, like he mixed the hard square and square well. He mixed the both and he got the function of epsilon sigma by r whole to the power v, which is nothing but if you take the common, this is constant, this is constant, and this is the only radius is changing between the two molecules. So then this is written as a to the power minus gamma, and the gamma is integer. And if you have the gamma is very less, it becomes the hard square. So it means the graph will go quickly like this, and if the gamma is more, it will go quickly like the soft sphere up to a certain extent. Then if we mix the both, okay, so no, there is no mixing here as of now. So by that's what he said, if you have the low value, it will become like a hard square, sorry, what is the name, I forgot. Yeah, hard sphere. And if you increase the gamma value, it will go to the square well. Okay, but here if you see, here we are talking about either attractive terms or repulsive terms. We are not originally keeping the two terms together. So to keep the two terms together, the LJ potential, which is the famous one, which is used in the current days. So this is epsilon, and this is the sigma. So here we have the both attractive and repulsive forces. So this is the best suitable one, and the formula for this is 4 epsilon sigma by r 12. So you can see that if there is attractive force, attractive means it is taking more energy, so it means it will go to the negative. So this is for the attractive, and this is for the repulsive, because the repulsive will have the higher force. So this is the Lennard-Jones potential, which is used. Say suppose you want to calculate the attractive and repulsive forces of the interacting atoms, non-interacting atoms. So this is like you need to remember this. So LJ potential is like, say suppose there is one water molecule here, and there is another water molecule here. So we are calculating between these two molecules. Okay, this is called as interparticle interaction. So we are not talking in between okay, we are talking between two different types of molecules. That's what we can calculate through either hard, what is the name again, I forgot, one second. Yeah, hard sphere, square well, or soft sphere, or LJ potential. If your focus is only either to see association or dissociation of any say of a protein or the ligand or anything, you can do these things, association of the biomacromolecules. But if you want to see the interaction between the two particles, you need to go for the LJ potential. So these all are for the short range. So it means when you have the two molecules together only, you can apply this rule. So once you have the long range, when you have the ionic charge on each particle, so this will come as Z1 Z2 by, one second, what's the formula, 4 pi epsilon naught R1 Rj. This is dielectric constant. and these are the partial charges of each atom. So why this is called as long range was you can have the ionic power to certain extent than compared to the small attractive or repulsive forces. So that's why we call it as a long range interactions, and there is short range interactions. So now, you have any doubts in this point? So you are for the pair potential of for pair potential. So pair potential means you are taking the interaction between the two atoms. Say suppose this is one atom and this is second atom, and you are considering the what can be the potential energy it can have. So that we can have it through short range plus long range. This is interparticle interaction. When you have the two different types of atoms, so any doubt in this?
No, sir.
So now we are done with the interparticle. Okay, it means we are done with the atoms. Now we will come to the molecules. So we are done with the atoms. I mean two different molecules or anything. Now we will come intra. So we'll come to the intra. Intramolecular interactions. We call it intramolecular interactions. Say suppose we have two molecules. I will write the oxygen and only. This is the one small example. So if you want to calculate the interaction between the potential energy between these two atoms or these two atoms, or say these two, because there are two together, so you can use the short range plus long range interactions. But what about these ones? What about the intraparticle? Like what is about this one and what about this one? So that things is called as intraparticle. So the differences we have was bonds, angles, dihedrals. Okay, say suppose assume it as there is a force system. Say I can write as 1, 2, 3, 4. So now here you have the interaction between the first atom to fourth atom. So there is an interaction between the 1 and 2. So you will get 1 and 2 bond interaction of 1 comma 2 plus u bond of 2 comma 3 plus u bond of 3 comma 4. Okay, so this we will write as sigma u bond, and then we have angle. If you see, there is an angle between 1 comma 2 comma 3, and there is an angle between 2 comma 4. This is dihedral actually, basically. So dihedral means when you have the different plane, we are talking about the different planes angles. So now the angle we have was 1 2 3. So this is the one angle, and then we have the 2 3 4. So this is one angle. So 1 2 3 and 2 3 4. 1 2 3 4. So 1 2 3 there is a one angle. So this is the one angle of this particular system, and then 3 4 we are having one angle. And assume that I don't know whether you can see me or not. So just use your thumb finger and little finger. Just keep it like this. So you have the L shape, and keep the both things. So now we have you can see. One second. Can you able to see me in the screen?
Yes, sir.
Okay, fine. So what I'm telling was, one second, yeah. Assume this is atom 1, atom 2, atom 3 and atom 4, and now 1, 2, 3, 4 is kind of like this, okay. So now so the angle is between 1, 2 and 3. So 1, 2, sorry, first one, the second one, the third, the fourth, and this is the bond, okay. So now I am rotating this bonds, okay. So it means this is in one plane and this is in one plane. So now we are rotating both the planes, right? So this is called as dihedral. So that's what you understand, right? What is dihedral?
Yes, sir.
So we are changing the position here, and then this will be dihedral, but the angle will be 1 2 3 and the 2 3 4. So this will be the angle. and there are different types of formulas for this. So now whenever you are talking about the molecules, so whenever you are taking the atoms, it is better to take only, so whenever you are taking the atoms, I mean if there are no interconnection between these two, then you have only interparticle interactions, where you will calculate UR with short range plus long range. Don't forget that we removed this one, okay, U bar, sorry, this one, U of R bar, where the interaction with the this one, okay. I mean this part we are not writing any case. I will explain you that how can we overcome it. For the molecules we need to take inter plus intra. So inter comes from short range plus long range, and the intra comes from bonds, angles plus dihedrals. So if I write this whole of UR, it will be U bonds plus U angles plus U dihedrals plus U short range plus U long range. So bonds, say that there are different types of formulas and which one you want to follow. As Sir said, Sir is following the Hooke's law, and there is a harmonic constant also. Harmonic constant, what does it do us? There is a harmonic constant, another one. So what does the harmonic constant do us? It's like it acts as a spring. So it will take the molecules and it will take this one. Okay, it acts as a spring and it will calculate the values. So as Sir said with the Hooke's law, so this will be sum of I. So k by 2. This will be k by 2. I'll write Ri minus Ri initial naught whole square plus, sorry, not Ri. Again you will get confused. We will go through the same nomenclature as R used. So Li minus Li comma R. So then I of k theta by 2 of, so then once again, I think I'm not making any mistake, yeah, plus so plus the short range is nothing but LJ interactions, and then long range is so any doubts in this whole equation?
No.
Sorry, I can't hear.
No doubt.
Okay, fine. So now say suppose there is your assignment question. I'm not directly explaining your assignment question. Sorry, one second. Assume that I have given one molecule system. Say suppose I have given the benzene, not benzene, take some CO2. So it will be of the 180 degrees. So now if you consider here, there is an angle term and there is a bond term. Will there be any dihedral term here? So I will ask the question in a different way. I mean this is for the example, how to solve the assignment question or how to understand this in a different way. So they asked the question for this one, right? What do you call for a hydrogen bond? If you remember. Hello. I think I'm still audible, right?
Yes.
So they have given the question for the hydrogen bond, but I can't explain the hydrogen bond. So I'm just taking the CO2. So hydrogen bond means nothing but OH, NH, where we have one high electronegative atom and one high electropositive atom. So I will explain you on example, then you can try to solve this. So now there is CO2. You know how CO2 stands? You know this one, right? Uh,
Yes.
now, now what it? So can you tell me what does it has? So suppose if I write UR, I'm talking about the only single molecule. I'm not taking that. I said that you have, in the system you have only one molecule. So then what are the how the UR will be like from this formula? You understand the question? Hello. So basically, what is the formula for UR? I will write the formula: bonds plus angle plus dihedral plus short range plus long range. So now tell me which are the properties will be involved here.
Dihedral bond will be there.
Sorry, I mean your voice is breaking. If I am talking about only one molecule, so which one to pick? Just tell me that this is 1, 2, 3, 4, 5. So if I want to find out the potential energy, so what are the terms I need to pick if I have only one molecule, one CO2 molecule? Out of these 5, can I take all 5?
No, sir.
So can you tell me which one I need to take? I mean which one I need to consider?
1 and 2.
1 and 2. So everybody understood what we are calculating. So now the UR formula will be sigma of k by 2 L1 minus L0 whole square plus. So now if you make UR with respect to 2, but here we have two different terms. So now you have the term with L, and here you are with theta. So now the total UR will be in accumulation of these two. Okay, if you make the graph, assume that you by yourself. Okay, I will explain it. So in the first microstate it is look like this. Okay. Hello.
Yes.
So now I am counting the terms: first term, second term, and third term. Now the bonds what you have here is 1 comma 2 and 1 comma 3, and angle is 312. Okay. So this will be 180 degrees initially. Are you there with me? This one up to here.
Yes, sir.
So now this is the first microstate. So now if you remember, we are going to this particle, this one. Okay.
Yes, sir.
And now assume that. So I will write it here. So I will make different microstates. So now initially you have taken the molecule from the, sorry, assume that n comma v comma t are constants. So don't assume that they are different size. So all the first microstate 3, 2, 3, 4, 5, 6, 7, 10. So m1 equals to m2 equals to and so on m10. Okay. So now you have the molecule. This is initial case, and the bonds also will be same. The bonds will be, assume it is, say suppose this is the initial condition I am writing here. It will be better. So now I am calling it as 1, 2, 3 atoms. So now bonds will be 1 comma 2 and 1 comma 3, and the angle will be 3 comma 1 comma 2 or 2 comma 1 comma 3. You don't need to mention two times here. Also 1 comma 2 is nothing but 2 comma 1. Either you need to mention only once, you don't need to mention two times. Okay, so I am not mentioning this one. So now what I am doing was, so this is the initial structure. In the next macro state, I have this one, and in another macro state I have this one. In another macro state, okay, in another macro, so you can see the differences. I'm just giving the heads up example. The bonds won't be bent, okay, you need to understand it. So now, so you understand what I'm writing here, the different macro states.
Yes, sir.
So now, if you have taken this system, so say suppose you have only 10, okay, and in this 10, if you want to calculate the potential energy, so what we need to calculate was the potential energy we can calculate, and by far you will get the original for this one. This is original one, and say this is might be original one, and this might be original one. Out of 10, if I take probability of the original location was 3, it means whatever the value you are getting for this low macro states will be is not equal to the original value. You got my point? That's why we said the probability one.
Yes. Yes.
So now, uh, can you tell me the, so now if I take the bonds here, it will be like, assume this is the values of, so now it will take was UR of sigma of macro state, so it will be, so I'm writing it is here, so U1 plus U2 plus U3 plus and so on plus U10, okay.
Yes.
So now you are writing sigma of Li minus Li naught square, right? So sigma, you got it right. So Li means this is the first one, Li minus Li naught square, so this is the value, plus the second one, plus and so on as usual. Okay, you understand my point?
Yes.
So now this is the way how we calculate. Say suppose if there are two molecules, I'm just writing, there is another molecule. So now tell me what is the properties out of this 5, what we can take. You understand my question?
So we have two molecules now.
Yeah, we have two molecules. Say suppose, so 1 second, I will write the formula: bonds plus angles plus dihedral plus short range plus long range. So if I have only one molecule like this, we have taken say 1, 2, 3, 4, 5, 1, 2. Now say suppose we have like this, and I will get third case also, and there is fourth case. So now tell me which are the, if I am writing the UR, so first one you know already, yeah. So for second case, what are the properties will be eligible? You understand my question?
Yes.
So yeah, and okay, 1 second, and there is fourth case. There is say suppose C. I just taken the carbon bits, okay. Hello. X. So these all are carbon bits, okay. I have taken the just bits of carbon. So can you tell me the different cases and what are the parameters will be helpful?
All 5 parameters plus second one.
For this case,
All.
sorry, one, one is acceptable.
Yes.
Two, So you can try to see figure out the answer. So my screen is visible, right?
Yes.
Yeah. So now, mm. So yeah, tell me. So can three we can apply here? So I'll say that 3 we can't apply here. Here also we can't apply the 3. Here we can apply all. Can you tell me here you can't apply first one, second one, third one. We can apply 4, 5. What is the sixth one here? If you remember the formula, we have if you remember this formula, there is one question in your you got my point, right? Why you can't use 3 here? Hello, my voice is audible, right?
Yes.
Yeah, fine. So see, dihedral, we can use the dihedral only when you are in the plane. Okay, so suppose we have 4 atoms, we can use the dihedral. Just assume it as if you have 4 atoms only. So when you are in the plane, when you can rotate it when you can rotate the bond such that the 2 atoms from one side will rotate to one direction and this two will rotate to one direction, then only you can apply the dihedral. Okay.
Okay, sir.
So now here it won't applicable, here it won't applicable, but here it is applicable. Say you can take any 4 atoms, 1, 2, 3, 4, we can rotate it. We can take 1, 2, 3, 4, we can rotate it. We can take 1, 2, 3, 4. This 4 is not a particle. Okay, you got my point, right? We can take
Yes.
only 4 attached atoms. So suppose this like this or like this. Suppose you have 1, 2, 3, 4, 5. We can take the first 4 as a dihedral, or say suppose 2, 3, 4, 5 also dihedral. Okay, here you have the 2 dihedrals. You got my point?
Yes, sir.
Yeah. So now the last case. So you have the first question in your assignment. Say I have I'm not saying I have 10 particles, and forget about the higher bond interactions. Okay. So what will be the UR? So you know this formula. Not pair potential. So this is formula is of you remember this formula, right?
Yes, sir.
So now if you have 10 particles, so the each particle will collide with the system, right?
Yes.
So now that will be 10 plus how many interparticle? Say suppose the first will have connection with 1, 2. It can have 1, 3, 1, 4, 1, 5, 1, 6. So it will have that 9 interactions. Okay, am I right? The first
Yes,
particle
sir.
can have 9 interactions. The second one can have 8 interactions. Okay, because 2, 1 will be omitted, right? Because 1, 2 is nothing but 2, 1. So it will start
Yes,
from
sir.
2, 3 to 4. Then 3 will have 7, 4 will have 6, 5 will have 5, 6 will have 4, 7 will have 3, 8 will have 2, 9 will have 1. Am I right?
Yes, sir.
So now the total UR will be, I mean, which one you need to consider was, so it is nothing but okay. So in this way you can solve your first question, the first assignment question. Okay.
Okay, sir.
Okay, just if you read it, and this for the second question also, we have discussed the properties here, right? Say suppose uh, if I given say suppose only C comma C, okay. Hmm? Uh, so can you tell me which one can applicable here for C comma C?
Bond is applicable.
Only one is applicable, right? So
Yes, sir.
now the formula for one is K by 2 L1 minus L naught whole square. Okay. So what does this L naught says was, see the whole equation, if I take the UR of this as L naught, okay, this will be stable at only one position, right? Because this is only bond is stable at only one location, right? Say suppose this value is, I'm just assuming that this is X, okay. If the value is X only, it is stable, right? It will be in the equilibrium, okay. Otherwise the bond will be like this or the bond will be like this, right? Which is not in the equilibrium position. So it means the value will be low here only. It is called as the minimum position, right?
Yes.
So now you have taken the minimum position and say suppose this value is X, I'm just giving, okay. This is the X and say suppose you are increasing to this side. So what it will become? X plus 1, X plus 2, X plus 3. Hello. And if you go this side, it will be X minus 1, X minus 2, X minus 3.
Yes, sir.
So now if I put this formula, say K by 2 is constant, forget about the K by 2 for some time. Okay. So now I am taking the three conditions. One is X condition, which is at the bare minimum, we know already this position. And how does the equation goes from here? Okay, say suppose if I take X plus 1, so X plus 1 minus X whole square. So it will be 1.
Yes.
You got the point, right? What I'm going to say here?
Yes, sir. Understood.
Yeah, so now if I take X plus 2, it will be X plus 2 also, it will be 4, then 9, then it will go like 16.
Yes, sir.
And this side also, if I take, it will be X minus 1 minus X whole square. It will be again 1, 4, 9, 16.
Yes, sir.
So now, I mean, you got it, right? I'm just giving the example and say suppose if I give the C11C slash O also, you can able to figure out, okay. Because here you have the two atoms, here you will have the bonds plus angles. So you need to figure out the formula and then you need to write that, okay, what will be if I increase and decrease.
Yes, sir.
Okay, so but this is not the case and you can do it separately for bonds and angles. And in this way you can solve your second question. Okay, and find out the values through online. Okay, what is the value for a basic hydrogen bond? And you can try this one also, okay. What is the basic distance between the two carbon atoms? Okay, single bond.
Yes, sir.
So now so you are understood, right? So we have, say suppose now we have the system. I think I explained it here if I'm not wrong. Yeah, say you have 10 microstates and if you have the 100, maybe at some point of time you will get this number more, the what you call the stable ones. If I go for 1 lakh or 10 lakhs, the stable configuration, this one will be more compared to all others, then the probability attaining will be more. So in that way the energy which is obtained by you will be in line with the experimental values. That's why we need to run for the longer run. That's where the ergodic hypothesis comes. I think ergodic hypothesis, spelling mistake if it is there, excuse me. So now you understand the meaning of ergodic hypothesis.
Yes, sir.
So now we are done with the ergodic hypothesis and the basic questions. Now we have the computer code. So you should I will explain you a few things. So if you want to remember the computer code or LJ or say suppose you will talk about the PBC anything, you can refer the book by molecular simulation by Franklin Smith. Okay, in this book they have written all the basic codes for the to run the system in Fortran, which you can further convert it to Python or C++. Okay, you can read this book for the computer simulations. Okay, molecular simulation by Frankel and Smith. This is one good book.
Okay.
Yeah. So now you know that LJ potential formula is sigma by r. So now then what we have is so how to write this. I think you will understand this from the class also. Just I am rewriting it. So we will read the values of x comma x, which is sigma epsilon, because these two are the constant values. Whenever you take a molecule, we have the sigma and epsilon values, and then you are initializing the value as 0 comma 0. Basically you write in the Python code, right? You will write initially u equal to 0, and then you will add the terms. So now in the Fortran we will use the for loop. In the Python we will use the for loop. In the Fortran you use the do loop. Do, there will be numbering. Suppose how many do loops are there. So do I equal to 1 to n comma minus 1, and now you will get the coordinates of because the r is depends upon the x axis, y axis, and the z axis. So now what you will get was rxi equals to reaction of ith coordinate, ryi equals to reaction of ith coordinate, rzi equals to rz of ith coordinate. Once you have these values, then you will apply the do loop inside the I loop. I mean for loop in the for loop. You can assume it like so. Now j equal to I plus 1 comma n. So now you need to get the two values, right? R comma ij. Rij is nothing but r2 minus r1 whole square, right? Here if you take it, so now I mean this is the value, and you need to take it on the all the three sides, on the x axis, y axis, z axis. So now if you have the z value, now rx, you can write this as rxij is equal to rxi, which is this one, minus rx of j, ryij equal to ry of I minus ry of j, then zij equals to rz of I minus rz of j. Now you have all the values. So now then we have we need to do the square root. Just so here we are applying the sigma also. Sigma square we are writing. So now we have the sigma. So now we write the sigma as sigma square as sigma into sigma. So now we have the rzx. Then we will have rij square root equals to rxij plus, so it's like distance between the two atoms. We will take, right, x1 square plus x2 square plus x square plus y square plus z square. We are doing the same thing into ry of ij into ry of ij plus iz into rz of ij. So now we have this. Then we will apply SR2, which is nothing but, so SR2 is nothing but sigma r, sigma by r square. Okay, this is nothing but sigma by r square. It is nothing but sigma square by rj square. So then SR6 means we are writing this value, SR2 into SR2 into SR2, SR12 equal to SR6 into SR6. Yeah, now U equals to SR6 plus SR12. Now we will update this, and then we will close the U loop plus U, this initial value. So now we will close the first this loop, and then we will close the I loop. Now we will get this value. Now the V equals to 4 into epsilon into U. This U will get it here, and then write this value to the main to here. So x comma v comma which value you are writing v, and then stop end. So basically we are doing whatever we are doing. So we are taking the xyz coordinates. You understood, right? So how we have done the calculations of bonds, the same way we are doing the LJ potential also. Any doubts in this equation? This is for the one system. You need to do for all that way. Like that's why you are using the loop, right? Any questions regarding this?
Yes.
Okay. So now I will explain you one more thing. See, suppose initially I said that if you have the box, okay, here we have discussed that if you remember, so like this, right? So now say suppose now we want to take the molecules. Say suppose I have taken 100 molecules which are randomly placed, okay. So now if you consider this particular molecule, okay, it will never go and reach the what you call wall, okay, but this molecule can go and reach the wall, right? Is it true? Hello, I think just get this idea. So this molecule can easily reach the wall. So say suppose I will pick this diagram in another way. Assume that you have different molecules. So single, assume that each entity can be a water molecule or CO2 or single atom. So now if I take this one, okay, now if I take this one, you understand my point? If I take this molecules, the value will be with, it will have the wall interaction, but this won't have the wall interaction. You understand my concern, what I'm saying here?
Yes, sir.
So now if I do this, then if you add the whole molecules interaction, so at the end you need to get the microstate total energy, right? So if you add it, the all the particles will not possess same energy, so that's why your value will not be equal to the experimental values or which you want to get it. So that's why it means what does it says was you have the molecules which has some another energy here which is not uniform. What I can say was it's not uniform. The another name which was given was surface effect. So it means the surface has some effect on the molecules which are on the surface. So to overcome this, we have taken the periodic boundary condition. Okay. So what does the periodic boundary condition was do was we will elaborate the same system in all the directions. So assume that this is the x direction. So this is our original box. I am expanding in the this direction. Okay, wait, I will put it in the small only. Just understand this concept, how we are removing the, so this is our main box. We are expanding it in the 3 dimension. Assume it is now becoming as cube. Okay. So now you increase the, I mean you just take the replicas. You got my point, what I'm saying? It's like if it is 1 here, it will be 1 here, 1 here, 1 here, 1, 1, 1, 1, 1, 1, 1. So it's like, say suppose you have the molecules like this, 3, 4, 5. As it is replica, it's like a mirror, like you just carbon copied it. Okay, any doubts in this?
No, sir.
So now what we will do is, say suppose I am taking only these three, okay? Just assume that I am taking these three conditions. I'll make it as a big box. So now say suppose we have the molecules like this, right? So what happens was, assume that this molecule has a surface effect, okay? It is coming this side, it means this will go to here in this box. At the same time this molecule will come and sit here, okay? Or this molecule at the same time, if it goes there, it means this also goes here. You got my point, right? What I'm speaking here. So it means
Yes.
the number of molecules will never have the surface effect here. Here there is no surface effect, okay? So it is just passing through the membranes, okay? You can't even call it as membrane. It is just, instead of the small box, now it will become the whole box of one microstate. You understand the basic concept of PVC? Hello. So but the limitations are this are, initially we have only 4 molecules. Now if you take this thing, 4 4 4 4 4 4 4 4 4, it's like 12 12 12 24 molecules, and you need to take the 24 molecules interactions. It is computationally expensive, right? So then they got the image convention, I think minor image convention or mirror image convention, I forgot the word. So what they do was, so you understand, right, my concern of PVC. The PVC is a good concept, but it is computationally expensive. Any doubts in this?
No, sir.
Okay. So now what the it is, I think, mirror image convention. What it does was, so it will come to say it will come to this state, okay, or it will go to this state, any state. It will take this molecule, and it will make, this will shift, the entire box will shift it to here. See, this box dimensions are 4 by 4 by 4. This box will be shifted in such a way that this will become the center, and for this will become the center, and for this will, suppose here, if I take this one, the box is shifted in such a way that this molecule will be in the center. If I take this molecule, you got it, right? So now we have taken for 4 molecules 4 different center boxes, we splitted it.
Yes.
So now if you see here, if I take here, there will be the, in the periodic, here we will have the image, right? This one, here also there will be one, in such a way that if you take this one also, there will be, this molecule will be there, this molecule is there, and this molecule will be, so it is 1 2 3 4, you can see it, right? Still we have 4 molecules. If I take the box, 1 2 3 4.
Yes.
So now what we have done was, so this has 24 molecule interaction. The mirror image will have the n into n minus 1 interactions. Okay, it means you are just interacting with one with through 1 2 1 3 1 4 2 3 2 4. Okay, you are, because you are making the boxes, right? You understood what I'm saying?
Yes.
But then there is another method, which is radius cutoff. So instead of taking this many interactions also, what they did was, so they made one small circles around this with some radius. I think this will be some confusing, bear with me for 2 minutes, you'll understand it. So if you take this molecule, they drawn the small circles with cutoff radius, which is not greater than the L by 2. I mean, not like greater than, say suppose the box is 4 by 4 by 4, it should not be greater than 2 by 2 by 2. Okay, up to there you can make such a size that you carry out your values, what the original values will not, okay, what do you call, the change much. So that's why the PVC condition and the mirror image convention, and then the radius cutoff. Okay, by using these values you are removing this one, this RT effect. So now if you take whole energy, the value is only this one. If you take any molecule, okay, any doubts in this? Hello? Unless until mention that it has the wall effects. If somebody says that it has wall effects, then you should consider it. If they didn't mention, it means you don't have it. Hello?
Yes, sir.
Okay, so now we have completed it and examples. So I will explain 2 3 examples. I think in the assignment questions also, I think I explained the first one, the second one, and the remaining questions are also very easy one. There is one, okay, just try it. I think they all are easy only. If you have any doubts, you can ask me in the assignment questions. Have you tried the assignment ones? Hello? Okay, you can try the assignment one. So examples, I think we'll have 2 more classes. I'll explain more in the examples on the MD protocol. I just want to show. Have you seen the sir lectures? Hello. I think I can write it here. Yeah. I think the screen is visible, right?
Yes, sir.
One second. I just want to see. I want to run this system. So can you see this system? It is fluctuating.
Yes, sir.
Yeah. It's fine. So first I will explain it. Then I will show you the diagrams. Basically I'm working on this field. So what I'm working, I will explain you that how it is helping in my systems. Okay, so what is happening was, say what I have done was, initially I have taken, say, have you heard about the thyroid cancer? Hello. So okay, I have taken one live example, I mean one real example of thyroid cancer, and there is one particular protein associated with it which is called as RET protein. Okay, and the approved drug in 2011, they approved one drug for which under the name of vandetanib. Okay, so then what is happening with the vandetanib was, so it is getting the resistance. Okay, the protein is attained the drug resistance. You know the drug resistance, right?
Yes, sir.
So now it has attained the drug resistance, and when I do the literature survey, I found out that because of in amino acids the RET protein, it has, suppose, around 240 amino acid sequence to 240 to 300. I don't remember exactly now. Say suppose assume it has 260 amino acids. In this, in 1 or 2 positions, the amino acid sequence is changing. So from valine to methionine, glycine to serine. Okay, at 2 positions. So due to these changes, the protein is not able to take the vandetanib. So the cure is not possible. So that's why there is only one approved drug as of now, the vandetanib. So what we have done was, so initially, okay, we understood that, okay, there are wild type. Now we have the focus on wild type, and there is a mutant type protein. Wild type, the vandetanib is working perfectly, and the mutant type, it is not working. Okay, so now we developed the drugs where we have shown that, okay, which, say suppose which molecule if I add to the vandetanib, so the vandetanib structure looks like this. More of like this. Okay, so now if I remove any parts, if I remove any fragments, can I able to increase the affinity of the drug. Okay, so this is my basic prototype, and then what I have done was I have modified some changes, and what I found out was I have made on a protein. This is a simulation box, so I said that this is the one macro state. Okay, you can see that, right? You can see the macro state, right? You can see the box, and this box is filled with water molecules. I have not seen it for the, so this is all filled with water molecules. So now what I run was I have run for the microsecond, 2 microsecond, 1 microsecond, and what I found out was I found out that okay, I have applied the funnel metadynamics. I mean, what we have done was we are saying that okay, how much time the drug is binding in the region and it is coming out of the region. So I will explain you that later part. So that we got the IC50 values. I mean, we got the binding affinity values. So initially we got some binding affinity value of the wild type protein with Vandatinib, because this is approved drug which will get IC50 value, and we match the IC50 value with the binding affinity using delta G equal to minus RT ln IC50, and then we compared our new molecule and we found out that the binding affinity will be better than the Vandatinib in the wild type and mutant type. So that's why we suggested that this molecule will be good, and we published the paper of this. So you understand the basic concept, right? Where we have used the MD simulation.
Yes, sir.
In the original cases, I mean, you can think of like this. I will explain another example also. So now, if I 1 second, I think, oh yeah, I can see it here also. I don't see whether I can. 1 second. I just want to show you some things here. So now, the you can see that the protein is shaking, right?
Yes, sir.
And you can see 1 second. I will make. So you can see this position. Okay, this is the binding region of the protein with the drug. We can see. 1 second, इसको क्या हो गया? You can see it is moving, right?
Yes, sir.
So now what we found out was okay, it has taken certain amount to stay inside and it is coming out, and you can see that the protein and the drug is flickering, right? You can see it now, right, correctly. Hello. Just assume that it is flickering, right? It's like a fast forward motion.
Yes, sir.
So what? Yeah, what does it says was each one shows one microstate. So it is in the time of 1 microsecond, right? I saved for at least I have 2000 frames, assume it, and each one replication is taken as a one snapshot. Okay, that is 1 microstate. You understand the difference in the microstate? So the box is entirely microstate, and the each flickering is 1 microstate. 1 microstate. I don't know why it is not working again. Yeah, you got it. My point. Understood the macrostate here?
Yes, sir.
So see, in the macrostate, everything is same. Okay, if I take first macrostate and second macrostate, the number of molecules is same, the protein is same, the drug is same. Okay, what is the difference is the position between the drug and the protein is different.
Yes, sir.
So the Ri comma Pi is different. Okay, so it means you have 6 coordinates. Changes in the x comma y comma z, momentum in the x comma y comma z. Okay.
Yes, sir.
So based upon this, if you run for the longer enough, I mean from the literature you will understand that okay, how much is long enough. So we have run that much time, and we found out that okay, the binding affinity of the original molecule is say suppose minus 6.5 kilocalories. We did this analysis with the experimental value, which is in line with the minus 6.5. Then we said that okay, our experimental results are correct, and then whatever the new molecule we are proposing, we propose one molecule saying that okay, this molecule can have the better affinity from the simulation point of view, and the experimentalists need to figure out that whether the molecule is good or not. Okay, this is one type of use you can use the MD simulation. Any doubts in this type of problem?
No, sir.
Okay, so this is second diagram. Sorry, I don't know whether it will work. So you can see the diagram, right?
Yes, sir.
So yeah, can you see the drug moving? I mean,
Yes, sir.
yeah, I'll explain it in the good way. So this is the one drug, okay. This is another work which we did. So this is doxorubicin, and this is nothing but the lipid bilayer, okay. So from the literature we can say that the doxorubicin is used for the breast cancer. This is the oral. This is a chemotherapy drug. So there are different types of drugs will be given while if the patient has a breast cancer. One of the drug is doxorubicin. I mean the doxorubicin is a scientific name. The market name will be different. Maybe it has a I think parallaxil something is there. So but from the literature we found out that the doxorubicin can't able to permeate through the lipid bilayer. Okay. So suppose the structure will be like this. You can see this is the cell membrane. Inside you have the nucleus. The drug should come from out and then it should enter and then it should break the molecule. But in this case of doxorubicin, it's not able to permeate the lipid bilayer. Okay. So we figure out that what are the possible ways that why it is not figuring out. So from the literature we found out that the basic reason is the cholesterol. Okay. I mean the more the fat accumulation on the lipid bilayer, say if you see we have the different types of colors, right. You can see the lipids are designed with the different types of colors, okay, which to mimic the original lipids. They are POPS, POPC, and there is cholesterol, and then there is PSM, sphingolipids. I mean there is certain uses of it, and then we made the system and we figured out that okay, one of the papers has given that the lipids of the breast cancer patient will be 36%. So then we designed the systems with different types of percentages 0, 18 and 36, and figure out that okay, whether if we move the drug inside the system, can it go inside, okay, how much energy it is needed. So suppose you can see the graph, I mean you can see the system, right. The drug is going inside this here, and
Yes,
then
sir.
it is going here, and then it is going here. So what we have done was, if you see it once, I will explain you later. So you are okay with the diagram, right? You have seen the diagram. Now
Yes, sir.
I will explain the, one second. So what is the today's class and how we can figure out that equation, okay. So now in the today's class, so first I will explain the problem, then you will understand how it is related to our today's class. So now I said that this is bilayer, right. This is bilayer, and we are pulling one drug molecule from here to inside, okay, up to center point, and we are seeing why it is not able to cross the membrane. For the higher cholesterol, that's what we are checking, right. That's what our objective, right, whether it can cross or not. So for that what we have done was we filled the membrane with 0% cholesterol, 18% cholesterol and 36% cholesterol, okay. So now what we have taken was, say now assume that I am making this diagram in this way. So this is lipid bilayer and the drug, it should go like this and it should go to center. So now what I have taken was I have taken one molecule here, so X, and this is Y, and U of X comma Y, the potential energy, say the X molecule is here because we are pulling the Y molecule, right. So now I started pulling this molecule, okay. So now, so again, so in this system it's all filled again, this is in the box, okay, and there is water molecule here. I didn't show a water molecule for the convenience, and this is one microstate. As it moves, it goes to different, you got my point, right, what I'm saying here.
Yes, sir.
Yeah. So now, the, say suppose this is here, and the lipid bilayer will be here, okay. This is the center point, X point, and this is the Y, and this all are the water molecules, okay. We can visualize, right, the diagram.
Yes, sir.
So now I am pulling the drug molecule from here using the method called as umbrella sampling, which we will discuss, I mean which is not necessary for this course, which is advanced method. But what we are basically doing was, I am pulling these molecules and I got something value like this. Okay, I will show it one second. If possible, I will show it. Work 2. One second. If it's good possible. Yeah. So can you see the screen?
Yes, sir.
Yeah. One second. My photo is gone. Mm. So yeah, in this diagram, what we are doing was, okay. So you are taking this part, right? So I'm explaining this part. Okay. Just assume that 0 to 4. Okay. This side. Okay. This part. Okay.
Yes, sir.
So now I'll keep this one of our original one, and now I will start writing the new slide. So now if you have seen the diagram, we have found out that there is a, so the graph is going like this. The first one, there is second one, and there is third one, like this, right? So this is 0. So if you see
Yes,
today's,
sir.
so this is nothing but E, and this is nothing but the sigma. So what I'm saying was, I found out that okay, this is at the 0. 0 is nothing but, okay, I will make it another. This is the last for today's class. Just bear with me. This is the lipid bilayer, and this is the center, and the drug is moving from here. Okay, and what I did was, so I kept the drug here, and we have started moving it up to this point. So what I found out was, I found out the curve like this. Okay. So what does it says was, near to the bilayer starting point, it has the more attraction. You need the more energy to pull the drug inside. Okay, when you have the higher cholesterol. Okay, when you have the higher cholesterol, the drug takes more time to penetrate compared to the lower cholesterol. You got the difference between these two. That's what we studied in the today's class. LJ potential. If you see the LJ potential, you remember the LJ potential, right?
Yes, sir.
This is the epsilon, this is sigma. So that's how we can correlate that. Okay, if we have more attraction at the repulsion forces, how much repulsion we need, how much the cholesterol is affecting. This all the cases, and in the next class we will discuss more about okay how to do the MD simulation. So this is the examples which we are doing in our lab. I mean, I thought to explain some other example which sir is not explaining for the snapshots. If you have any doubts, you can ask. If you have any doubts on the statistical mechanics, I will explain it. You understand, right? The basics
No
of
doubts.
macrostates, microstates, the ensemble approach, the thermodynamic probability.
Yes, sir. Understood.
Okay, okay, then fine. Thanks for attending the class, Fahima, and others. You can leave. If you don't have any
Thank
doubts,
you,
you
sir.
can leave. Thank you for attending the class.
Thank you, sir.
Thank you.